Hello, Math 137 friends. Welcome to Chapter 6. We're going to start with 6.1, an introduction to factoring. I can't emphasize enough the importance of factoring in this course. You want to be a good factorer. Much of the material that we cover later on is going to depend heavily on factoring. So you definitely want to be good at this. If you are struggling, please ask questions. All right, what is factoring? Well, factoring is the opposite or the reverse of multiplication. So when we undo our multiplication, we are factoring. What do I mean? Well, we know that 2 times 6 is 12. All right, so what we did when we go in this direction is multiplication. If we go in the other direction, we start with 12 and we break it down into 2 times 6. Going in this direction, it's called factoring. 2 and 6 are both factors of 12, so we broke 12 up into its factors, 2 and 6. But is this completely factored? Okay, well, what do I mean by completely factored? Is that can we break up 2 or 6 any further? Well, we can. 2 times 6 can be broken up into 2. Well, 2 is completely factored. It's a prime number. Its only factors are 2 in itself and 1. 6 can be broken up further into 2 times 3. So once we have a numerical value broken up down into all prime numbers, it is now completely factored. So this, we would say, it's completely factored, right? All factors are prime numbers, right? We can't break 2 or 3 down any further because its only factors are itself and 1. So anytime we're factoring, we want to break our whatever is handed to us down into its prime factorization. All right, well, this is arithmetic, and this is an algebra class. So how does factoring in algebra differ than factoring in arithmetic? Well, the difference between algebra and arithmetic is variables. We are introducing variables. So let's look at this product, 6 times the difference x minus 2. So if you remember the distributive property, when we have a numerical value outside or anything outside the parentheses, we bring it in, we multiply it by each of the corresponding entities. So 6 times x would be 6x, so 6 times x would be 6x. We keep the sign, minus, and then 6 times 2 would be 12, right? So this is the distributive property, and the distributive property is multiplying. All right, so what we're going to do is factoring, and it's going to be the distributive property in reverse. So if we are given 6x minus 12, we want to put something out front and get those parentheses back. Right, so we look to ourselves, what can we factor out? And if we look above, we can see that the 6 pulls out. So then we say, what do we put in the parentheses? Well, 6 times what is 6x? And it would be x. Keep the minus sign, and then 6 times what would be the 12? And it would be 2. So now we can always check, which is great about factoring, because we can multiply through. We get 6x minus, and then 6 times 2 would be the 12. And we say, we're good. All right, notice we could have also written this. We could have done 6x minus 12. We could have pulled out the common factor of 3. If we pull 3 out, well, what would go first in the parentheses? Well, what times 3 would give me the result 6x? Hopefully you said 2x, because 3 times 2x is 6x. Keep the operator, and then 3 times what would be 12. So 3 times 2x minus 4 also gives us this expression factored. The problem is that 2x minus 4 is not completely factored. So just like when we broke 12 down on the previous page into 6 times 2, we can break the 2 down even further. We want to break this down even further. So if I ignore this 3, notice 2x minus 4, well, the term 2x and the term 4 share a common factor of 2. So I could pull the 2 out. And then what would left be? Well, 2 times what is 2x? X. Keep the operator. And then 2 times what would be 4 would be 2. So 2 times x minus 2 would give us 2x minus 4. And now when we look in the parentheses, there's nothing we can pull away from the x and the 2 nicely to give me x minus 2. But then don't forget, this 3 was out front, so that's got to come down along for the ride. So we would have 3 times, and we replace 2x minus 4 with 2 times x minus 2. And we multiply these two together, and we get 6 times x minus 2. So our goal is to avoid this step in the middle. So we want to pull out the greatest common factor. We would want to look at this and notice that 6 is a larger number than 3, and we want to pull out the greatest common factor. So GCF, which is the greatest common. Now I won't write that again. I will write GCF. So our goal is to always pull out the greatest common factor. All right, so let's just remind ourselves about finding greatest common factors of numerical values. So the greatest common factor is of 2 numbers, or 3 numbers, or 4 numbers, is a factor they have in common, and it's the largest factor they have in common. So if I asked you to find the greatest common factor of 36 and 60, well, back in our algebra days, our arithmetic days, would write all the factors of 36 and would write out all the factors of 60. So I've written them out for you. So the factors of 36 are 1, 2, 3, 4, so forth and so on. Factors of 60 are 1, 2, 3, 4, so forth and so on. So let's see what factors they have in common. They always have a factor of 1. They both have 2. They both have 3. They both have 4. That has 5. This has 6. That has 6. 9 is a factor of 36, but not 60. Ooh, 12. Right? 18, 36. All right, so those are our common factors. The largest of the common factors would be 12. Right? So the greatest common factor would be 12. Right, so writing out factors can be a pain in the neck, especially if these numbers are really large. You may miss some. So here's a cool trick that I've learned when I'm trying to find a greatest common factor. I don't care how you do it, as long as you can do it, but this always works. If you take a number, if you take your 2 numbers, start with one of them, and write out its prime factorization. And if you remember doing factor trees, so 36, you take any 2 numbers, when you multiply them, you get 36. I'm going to do 18 times 2. You could have done 6 times 6. Then look at your 2 factors that you created here. If they're not prime, break them down further. I can break 18 down into 9 times 2. 2 is prime, so that's just going to go down for the ride. So 36 can be written as 9 times 2 times 2, but 9 is not yet prime. I can break 9 down further into 3 times 3, and then the 2's just come along for the ride. So there's my prime factorization of 36. 36 can be broken down completely into 3 times 3 times 2 times 2. Now let's do this for 60. You can start with any 2 numbers. I'm going to do 4 and 15. You could have done, don't do 60 and 1, because then you're right back where you started. Make sure your first factor is at least bigger than 1. If it's prime, then it won't be able to be broken down any further. So 4 times 15. And then ask yourself, can these be broken down further? Of course, 4 can be broken down into 2 times 2. 15 can be broken down into 3 times 5. So the prime factorization of 60 is 2 times 2 times 3 times 5. And I know I'm done because each of these numbers are prime. That is, the only factors are 1 in themselves. Now, when we get to this point, circle what they have in common. In other words, I have a 3 here and a 3 here. Once you circle it, you can't use it again. So this only has 1, 3, so we identify and match it up with the 1, 3 over here. Can't circle that guy because there's no other 3 over here. We have a 2 here, so I can circle this 2 and match it up with that 2. or the other one, it doesn't matter. I have a second 2 here. I also have a second 2 here, so I can circle those. So once we look at the prime factorization, circle what they have in common, we just take the product of those numbers that we circled. The greatest common factor would be 3 times 2 times 2. So just take the set from one of them. The set will be the same. And 3 times 2 times 2 is 12. So the greatest common factor would be 12. So either way you do it, you can list the factors. You can use this cool little factor tree and go that route, as long as you get the greatest common factor. All right. I like this because I think it helps explain greatest common factors in algebra. All right, so moving right along, let's find the greatest common factor of 5b to the 6th and 15b squared. Maybe you know the answer offhand, and that's great if you do, but I'm going to do it. I'm going to break it up using my little factor trees. If I use my little factor trees, 5b to the 6th is going to be broken up 5, and then b to the 6th can be broken down as b times b times b, and I'll never do this again. I'm just going to do it this one time, right? 1, 2, 3. That's what 5b to the 6th means. And let's look at 15b squared and break it up. Well, 15 is 5 times 3, and then b squared is just b times b. So if we go along with that idea from the previous example, I circle what they have in common. They both have a 5 in common. Can't circle the 3. There's no 3 over here. But this has 2 b's, so I can circle any 2 b's over here. All right, so then the answer is the greatest common factor is 5 times b times b. And then we typically combine our variables and call it 5b squared. All right, so that was a little tedious. Okay, the numerical value in a greatest common factor is the greatest common factor of the coefficients of 5 and 15. And then if you have variables, right, look at the powers on the variable 6 and 2. A common factor of variables to a power can't be larger, can't have a power larger than the smallest power of the variables. So in other words, there was only 2 b's here, and no matter how many were over here, they could have at most 2 in common. So this is the smaller of the powers on like variables. All right, so what do I mean by that? Let's look for the greatest common factor of m to the 7th, m to the 5th, and m to the 12th. Well, they all have base m. We pick out the smallest power, and the answer would just be m to the 5th. We can't pull out more than 5 m's from here. That's the most that are there, so we can't use 6 m's because there's only 5 there. So look for the smallest power. And this also holds when we have multivariables, right? We have the variable x in each of the 3 terms, and we have the variable y in each of the 3 terms. So they're going to have a common factor of x to a power. So we look at the powers on x and choose the smallest one. So it would be x squared. They each have a y. And then the smallest power on the y's, well, we have 5, 7. And remember, if you don't see a power, it's understood to be 1. So the smallest power would be 1. It would be x squared, y to the 1 power. Now, typically we wouldn't leave it like this. I'm not sure how picky Alex is. Y to the 1 power is just y. So we typically do not write in that power of 1. All right. Continuing right along, the greatest common factor of 36z to the 8th and 60z to the 5th. What we just did previously, let's first find the greatest common factor of 36 and 60. And we know that that was 12. We just did that a couple of pages ago. So it's 12. So this is the GCF of 36 and 60. All right, and then it's going to be times z to the 8th, z to the 5th. We go with the smaller power, z to the 5th. The smaller power. on the z's. All right, well, we're going to take it up a step. We're going to find out how to factor the expression 36z to the 8th plus 60z to the 5th. Here, we were just looking for the greatest common factor. Now we're going to actually factor this sum. So when we have more than one term separated by addition or subtraction, we look for the greatest common factor. So we just saw that the greatest common factor of 36z to the 8th and 60z to the 5th is 12z to the 5th. So that's what we pull out. So this was the GCF of the terms. Okay, and then we insert parentheses. If you start with two terms, then you will have two terms inside the parentheses. All right, and we will keep this addition. So now we have to ask ourselves, what would we put here such that if we were to redistribute, we would get 36z to the 8th. So 12 times what would give me 36? Well, we would need the coefficient of 3 to get the result when we distributed to check our answer. So 12 times 3 would give me 36. And then z to what power, right? We have 5 z's here, but there's 8 here. So the power you put on z here is the difference between the 5 and the 8. So there's 3 left over that we didn't take out of there. So now notice if we multiply these two together, we get 36 z to the 5th times z cubed. You would add the exponents and you'd get z to the 8th. All right, now let's look at the second term. If we took a factor of 12 away from 60, 12 times what is 60? 5, right? Well, z to the 5th, we took away all z to the 5ths. So there's no term z here. We took all them away. We could put z to the 0 because there would be none left, but we don't. We just leave it like that. That wouldn't be considered simplified. So my answer would be 12z to the 5th, which is the greatest common factor of the terms. And what would be inside would be 3z cubed plus just plain old 5, because 12z to the 5th times 5 would give me the second term of 60z to the 5th. That's it. All right, let's look at this guy. This is looks like a very simple problem, but often the simple problems give us the most trouble. Factor 7 minus 14p. Well, the answer would be, well, we look at the numerical parts. The greatest common factor of 7 and 14 is 7. The only factors of 7 are 1 in itself, and 7 also happens to be a factor of 14. So I'm going to pull out the greatest numerical coefficient factor, which is 7. There's p's here, but there's no p's here, so we can't take p's out unless p's appear in every term. So now I'm going to have 2 terms left in. I started with 2 terms. I should have 2 terms left in the parentheses with subtraction. So 7 times what? What is going to go here such that when I was to redistribute to check, I would get the constant 7. Right? Be careful here. This is where students make mistakes. They think because we took the factor of 7 away that a 0 would be there, but that's not true because the other factor, when we take 7 away, 7 is 7 times 1. What's left is a factor of 1, and we need that 1 to hold the first place in the parentheses. We need to have 2 terms here separated by subtraction. And then this would be, well, 7 times what is 14p? Well, 7 times 2 is 14, but then we have to account for that p. So remember, you can always check. 7 times 1 is 7, minus 7 times 2p, which is 14p. Those lines don't mean anything except that I've just completed the problem. All right, let's keep going. Factor 22 x to the 8th y cubed plus 11xy to the 10th. All right, so my answer. Well, let's look at the numerical parts first. 22 and 11, any common factors? Well, 11 is prime, so only 11 in itself, but 11 is a factor of 22, so I can pull the 11 out. They both share a factor of 11. Both terms have an x, so I can pull x's out, and I look at the smaller of the two powers, remembering that if we don't see a power, it's assumed to be 1. So we're just going to pull one x out, and I'm going to leave, well, I'll put it here for now. And then both terms have y's, so we can pull y's out. 3 and 10, we take the smaller of the two powers. Right, now we put our parentheses. knowing we started with 2 terms, there'll be 2 terms in the parentheses. Right? What times 11xy cubed will give me 22x to the 8th y cubed? Well, let's start with the numerical part. 11 times what is 22? Hopefully you said 2. Well, I took 1x away from the 8 x's, so that's going to leave me with 7 x's. And then I took all 3 y's out, so y cubed is out front, so there's going to be no y terms left in the first, no y factors left in the first term. All right, we took the 11 out, so there's only a factor of 1 left, 1, right? We took the x out, but we only took 3 of the 10 y's out, so there's 7 y's left. Now, no, we're going to clean this up. I'm not sure how Alex liked this. Usually it's pretty picky. We usually don't write x to the 1 power. We simplify that to just 11 times x. Have to leave the power of 3 on y. 2x to the 7th, and we typically don't include a coefficient of 1. So if it's 1 times something, we eliminate the 1, and we're going to just call that y to the 7th, okay? All right, let's look at a couple more. Let's factor 4xy minus 6x squared y plus 2y. So now we have 3 terms. Right, so we look at the numerical parts, 4, 6, and 2. All share a common factor of 2. So we'll pull out the 2. We have an x here and an x here, but no x's here. So we can't pull something out unless all the terms in the expression have it. So we may not pull the x out. But all terms have a y, so we can pull the y out. So we've exhausted all 3 pieces. We're going to put parentheses. Right, it's going to be 3 terms with the subtraction, then addition. Right, so what times 2y will give me 4y squared? Well, we need the 2 to get the 4. We pulled out the y, but we have the x left. Again, remember, you can distribute and always check. 2y times 2x would give me the 4xy. 2 times 3 is going to give me the 6. We have x squared left. Right, and then the y, we pulled out the y. Now we pulled out the entire 2y, but remember, if we were to redistribute, what would need to go here such that when I multiplied these, I got 2y? We have to have something in all 3 spots. It's not 0, even though we took that whole thing away, because the factor that we don't see is 1. If we put 0 here, then when we redistributed to check it, we would get 0 and not 2y. So if you pull out the entirety of the term, we hold that spot with a 1. All right, here's where things can get a little tricky, and this is where it's important to follow directions. We have a negative here. So what happens when we have a negative? Well, we could still pull out 2y. If we pulled 2y out here, now be careful, we have to account for this minus 4 right here. So this would be minus 2 to start, and then we don't pull out the x, and we pulled out the y. So we'd have negative 2x here. So 2y, we have minus 2y times 6x squared y would be minus 3x squared. And again, you can distribute to c. And then we would have the plus 1. Right, so this is one answer. So make sure you always check by redistributing, at least mentally. 2y times negative 2x would be negative 4y squared. 2y times minus 3x squared would be negative 6 x squared y, and then the 2y and the plus 1 would give me the plus 2y. Or another answer, right? We may pull out this shares a factor of the 2 and the y, but we may pull out a negative 2. So what happens if we pulled negative 2 out instead? Well, we have to be super careful with our signs here. If we pull negative 2 out instead, I'm going to hide that. Well, we pulled out the negative, we pulled out the y, so what would be left would just be 2x. Now again, remember, you can redistribute and check. Negative 2y times 2x would be the negative 4xy. Now be careful, because this term, now things get a little bit tricky here. If we pulled the negative away from this, what could we have to put here such that if we were to redistribute, we would get negative 6x squared y? Well, hopefully you said plus 3x squared. Now again, mentally distribute, negative 2y times positive 3x squared would give me the necessary minus 6x squared y up here. Now my last term is plus 2y, so I have to think, what am I going to put here such that when I distribute negative 2y, it turns into a plus 2y? Well, how about minus 1 instead of plus 1 in the previous problem? So negative 2y times negative 1 would give me the positive 2y. So which answer do we do? Well, just follow the directions, okay? If it doesn't specify, either one or these are perfectly correct. But this one is factoring out a negative leading coefficient. So if the directions say to factor out a negative leading coefficient, then it wants you to take the negative out. Usually we do that when we start with a negative in our original expression. If it doesn't specify, then either answer is perfectly correct, okay? All right, so one more thing we have to talk about here. Let's look at this easy little problem. Factor 2xy times 5y, w squared y. Now notice 2 and 5 have no common factors. We have an x here, but no x's here. We can take a y out of each of them. Can't take out any w's because that guy doesn't have any w's. The only thing they have in common is y. So we're going to pull out the factor of y, and then what's left would be the 2 and the x from the first term. We're going to subtract, and we would have 5w squared from the second term. All right, now take a look at the next problem. Looks very similar to the other problem, the first problem. We have 2x times something minus 5w squared times the same thing. The same thing this time just happens to be the star. No one said we have to use just letters and numbers. So they share the star. I can pull the star out, and if I pull the star out, what's left is the 2x minus 5w. 5w squared, right? So that's that, that's that. All right, so I said it can be 2x times anything minus 5w squared times the same thing. If it's the same thing, if what this is the same thing, we can pull it out front, as long as it's the same. If I had a square here and a triangle here, I wouldn't be able to pull it out. But here I could do square or rectangle times 2x minus 5w squared. And no matter what's in here, as long as what's in here is the same, then I would pull that out front. So if it was 2x times smiley face minus 5w squared times smiley face, I could pull the smiley face out, and it would be 2x minus 5w left in the parentheses. Oops, typo. Take this out before I give you the notes. So cross that y off. That's the typo. Right, so if I say factor 2x times something minus 5w times the same thing, notice, cross that y out, typo, sorry. Right, notice they share a plus 3. They have this in common. So they have the parentheses and the expression a plus 3 in common. So what I'm going to do is pull out the a plus the 3 in the parentheses. So if I pull out the parentheses, because each of these terms, we have two terms here separated by subtraction, we pull out the a plus 3, and if I pull out the a plus 3 and then insert my parentheses, we're going to have the 2x left here minus the 5w squared left there. So no different than the previous three problems, but instead of a y here, which don't ignore that, sorry, instead of a star or a box or a smiley face, we have a plus 3 in the parentheses. So I pull the whole a plus 3 in the parentheses out, and what's left is still the 2x minus 5w. Keep going. So now let's suppose I have 12 times the quantity x squared minus 5 plus 4y times the quantity x squared minus 5. So notice we have two pieces here separated by addition, and these two pieces contain the difference x squared minus 5. So what we're going to do is pull the x squared minus 5 as well as the parentheses. You have to include the parentheses because that's all part of the deal, out. Once we pull those out, we insert a new set of parentheses. And if I imagine just hiding these, I take away the x squared minus 5, what's left is the 12 and the plus 4y. So that's what's going to go left here, 12 plus 4y. Now we have to be careful because you always have to look what's left inside the parentheses and ask yourself, can we factor any further? Notice that 12 and 4y share a common factor of 4. So let's pull out a 4. So from this, I'm going to cover this up, I can pull out a 4. When I pull out a 4 here, because they both share a common factor of 4, we have a factor of 3 left, and then we just have the y here. And then this x squared minus 5 is just going to still hover out front. Now we typically don't write it in this order. If we have just a factor that's is a singleton, or we call it a monomial, we tend to pull that out front. This is not incorrect, it's just not visually pleasing. X squared minus 5, and we'll do 3 plus y. So 12 times x squared minus 5 plus 4y times x squared minus 5, completely factored, is 4 times x squared minus 5 times 3 plus y. All right, this is leading to something bigger and better. Let's look at this 4-term expression. 2ab minus 4a squared plus 3b minus 6a. If we look at the numerical coefficients, 2, 4, 3, and 6, we can only pull out a factor, a constant factor, if they all have that factor in common. 2 is prime, 4 and 2 share a factor of 2, but 3 does not share a factor other than 1, and we don't pull out a 1 because we would keep doing that repeatedly and it doesn't make sense. So there is no common factor of 2, 4, 3, and 6 other than 1. Now remember, all the terms have to share the common factor. We have an a here and an a here, but no a's here, so I cannot pull out any a's. Let's look at the b's. Well, we have a b here and no b term here or here, so we can't pull out any b's. So this seems to be not factorable. When an expression is not factorable other than 1 in itself, we call it prime, just like prime numbers. But before we conclude an expression is prime, notice we can do this really cool thing. Let's look at this in pieces. Let's suppose I just look at, we notice 2ab and 4a squared. We can factor this. 2ab minus 4a squared shares a common factor of 2. And then there's an a in both terms, so I can pull the 2a out of the first two terms. And when I pull the 2a out, what's left is the b from here, minus, well, we have the 2 from the 4 and 1a left over, minus 2a. All right, well, let's look at the second part for a minute. Look at 3b minus 6a. They share a common factor of 3. So if I pull the 3 out, notice what's left. B from here, we do subtraction. If I pull the 3 out, we have the a still, and we have a factor of 2. And I'm going to keep this sign in the middle. So 2ab minus 4a squared plus 3b minus 6a can be written as 2a times b minus 2a plus 3 times b minus 2a. Oh, did you notice something? Woohoo, look at this. These two new pieces that we created share the factor b minus 2a. So we can pull the parentheses and the b minus 2a from each of those terms. And if we cover them up, what would be left would be the 2a and the plus 3. So we'll put 2a plus 3 in the parentheses. So what we did is we completely factored this term. You might say that's a lot of work. There is a reason for factoring. Factoring is a very useful tool in math. It will be very useful in this class as well as any upper level math class you take. Notice you can check. How do we know if we did it right? Well, b minus 2a times 2a plus 3. We FOIL. We get the product of the first. which would be 2ab. We always put our letters alphabetical in expressions or terms. B times 3 would be plus 3b's. Let's do my inners. Minus 4a squared. And then my lasts would be minus 6a. Is that what we started with? 2ab. Well, we have minus 4a squared, which we have here. So our order is different, but the sign to the left is the same, and that's what's important. So we have our minus 4a squared plus 3b minus 6a. Right, so remember, one great thing about factoring is you can always check your answers by multiplying. Right, what we just did is we looked at this 4-term expression. It originally appears to be prime because as is, the 4 terms have nothing in common. But if we look at them in sets, the first 2 and then the second 2 pull out what they have in common, we saw that we created a term that both of these little groups have in common. This process is called grouping. All right, so before you do anything, when you factor, you always try to pull out a greatest common factor first. Once you pull out a greatest common factor, if the remaining expression has an even number of terms left and 4 or more terms, then try grouping. So here we have a 4-term expression. Right. Notice 32, 12, 24, and 9 don't have any. Do they have any common factors? Nope, because these 3 share a 3, but that one doesn't have a factor of 3. We have an A here, but no A's here. We have a P here, but no P's there. Right, so as is, it does not look like it's factorable. But before you conclude a 4-term, 6-term, 8-term, so forth and so on, it has to have an even number of terms, is not factorable. Let's try grouping. So I'm going to look at the first 2 and see what they have in common. 32 and 12. Well, the greatest common factor, if we think of the factors, I always go with the smaller number. These both have a factor of 2, factor of 3, but not there. 4. Right, so 4 is a factor. 6 is a factor of 12, but not 32. So the greatest common factor of 12 and 32 is 4. And then they both have an A. So if I look at the first 2 terms, I pull out 4a, and what's left is 8 minus 3p. Now thinking ahead, I'm going to want an 8 minus 3p here to make this work. Does that happen? Well, what's a common factor of 24 and 9? There's no variable to pull out because this one doesn't have any. Well, the common factor is 3, and we're hoping for 8 minus 3p. If not, then we cannot group, or we might have to do something different. Well, 3 times 8 is 24, and does minus 3p work? Make sure you check. 24 minus 9p. Woohoo, it works. And then now, when I broke this up by grouping, right, because I looked at those 2 as a pair, the first 2 as a pair, and the second 2 as a pair, what they have in common is the 8 and the minus 3p and the parentheses. Make sure you take out the whole thing in the parentheses, and we insert a new set of parentheses. We take away the 8 and the 3p. What's left is the 4a from the first term and then plus 3 from the second term. There we go. So these have to be the same in order for this to work. All right, and make sure you check these. And this is always a great idea on a test if you have the time to make sure you go back and check. All right, one more problem. Let's look at 3mn plus 30 minus 18m minus 5m. Right? 3, 30, 18, and 5 have no numerical common factors. We have an m and n here, but nothing there. So as is, we cannot pull out a greatest common factor. So I'm going to try grouping. I can see right away that 3mn shares a common factor of 3 with 30. That's it. So it'd be mn plus 10. And interesting, we would need mn plus 10 here. And we try to pull something out of here. Well, this doesn't have an n, right? So that doesn't work. All right, well, it's a 4-term expression. At this point in the game, you can pretty much guarantee if you have a 4-term expression and there's no greatest common factor, that they're probably looking for you to group. All right, so as is, grouping didn't work. Right, so we can try rearranging. So if we rearrange the terms, maybe we can get this to group. So I'm going to leave the 3mn alone. And I notice 18 shares a common factor with 3, and so does m. So I'm going to take the 18m and always take along the sign to the left. So it has to be minus 18m. And then I'm going to leave the plus 30 minus 5n and see if this helps at all. So now when we group, and sometimes you have to try grouping more than once, 3mn minus 18m, we can pull out the 3 and the m, because 3mn, 3 and 18 have a common factor of 3. They both have an m. So we pull the 3m away from the first term. What's left is n. And then if we pull a factor of 3 out of 18, we get 6. We took the m out. So n minus 6 was what would be left. So we're hoping to see n minus 6 over here. If we can't do that, then we have to try something else perhaps. So if we look right here, right, well, they share a common factor of 5. So if I pull the 5 out, I'm going to get 6 minus n. Now be careful, n minus 6 is not the same as 6 minus n. All right, so now here's the trick. Anytime you have a factor close to what you want, and if it was addition, we could switch the order. We cannot switch the order in which we subtract. So the cool trick here is when you want to, you have a factor and you want to switch the order because we want n minus 6, all you need to do is switch the sign in front of that term. So what do I mean? We are going to rewrite this as 3m. We want n minus 6. And instead of positive 5 times 6 minus n, I'm going to change that to minus 5 and n minus 6. So that's called the polynomial's opposite property. So this is my cool trick. Right? It's called the polynomial opposite property. Polynomial opposite property. The polynomial opposite property says whenever you want to reverse the order in which you subtract, if you have a minus b, you want b minus a, pull a negative out front, and you can switch the order in which you subtract. Because if you just distribute, you'd get negative b plus a. Right, so that works here. So in order to switch the order of subtraction to n minus 6, instead of pulling out a positive 5, I pull out a negative 5. So now we're at 3m n minus 6 minus 5 n minus 6. We can pull out the common factor of n minus 6, and if I take the n minus 6's away, we are left with 3 minus 5 as my second factor. All right, so to do, check. Make sure this gives me what I started with. All right, kids, I talked for a long time, so I'm going to let you go work on some of these problems. Make sure you bring questions to class. See ya. Have a great day.